Okay. Hello, everybody. It's 3:30 here in Colorado. Hello, everyone here in the room, and greetings to the people following the broadcast streaming. Welcome to the 2022 ECOM seminar series, and it's an honor and a pleasure for me to introduce Stanislaw Cieslik. He got his PhD at the Belgian Space Aeronomy Institute. His thesis was focused on upper atmosphere spectroscopy, in particular on the photodissociation of nitric oxide. He has later been working at the Joint Research Center of the European Commission from 1983 to 2013, and his activities were focused on air chemistry, boundary layer processes, using mostly eddy covariance technique. He's a visiting scientist here at Anchor from May to the end of the month, and today he's going to talk about his research focused on air-vegetation exchange, especially ozone fluxes, and the potential damage to vegetation, including stationarity problems. I want to remind people following in the streaming that you can enter your questions in the window below the video. And for the people here in the room, please help me welcome Stan on the stage with an applause.
Okay, welcome to everybody. So thank you. Okay, microphone is there. So thank you, Alessandro. So I am here a visitor, and I'm going to speak with you with the work we did in Europe about air vegetation exchange, micrometeorology, and since I am here, I am working on stationarity, and this is a continuing work. So I worked for the Joint Research Center, which is a scientific institute which acts as a scientific advisor to the European Commission, which is the governing body, the executive body of the European Union. So the executive body of the 27 member countries. And this JRC is located in Ispra, which is a small town in northern Italy, not far from the Swiss border and from the foothills of the Alps. And the research activities are mainly focused on environmental problems, air, water, soil, waste, pollution, climate change, food security, and related topics. One of the topics we studied is focused on air vegetation chemical exchange processes with an eye on plant damage due to air pollutants. A part is also devoted to the greenhouse gases, which is, of course, an issue today. Particular attention is put on ozone because it is now recognized as the major phototoxic pollutant among all pollutants for the plants. So ozone phototoxicity affects crops, natural vegetation, forests, and so on. And you can see here the visible damage that ozone causes to leaves of various kinds of trees, of course in variable measure because several species are more resistant and other more sensitive to ozone attack. But the damage is not only visible, the important damage is on interference with photosynthesis, which causes a slowdown of growth of the trees and also every kind of plant. And as a consequence, there is less carbon sequestrated by plants, as this has been the object of various studies. So we use different methods to assess the ozone risk to plants. Micrometeorology, open top chambers, branch enclosures, and also subflow measurements in trees. We will explain that now. And we collaborated with universities, research institutes, and everything was coordinated at European level. So this is just to mention it, eddy covariance and micrometeorology. Everybody knows about these techniques, I think. Then we have the open-top chambers, which are consisting in portions of vegetation of one single species, enclosed in cylinders of plastic with a cylindric structure, but it's not necessarily cylinders. And we measured, well, then they are fumigated with a known gas like ozone, for instance. And so we can measure the effects on the plants, on the growth, and so. Then there are also cuvettes or branch enclosures where you enclose a branch of a tree. In this case, I think it was a beech. And to study gas exchange with whether static or dynamic techniques. Then there is the subflow measurement technique is quite interesting because it puts in relation the evaporation, which comes from the leaves, of course, and the flow of the water pumped from the roots, of course. Of course, there should be a relationship between the two, because that water coming from the ground level, from the soil, is going up in the tree and ends up in evaporation, of course. So there should be a relation with the two. And we will see then that to study the penetration of pollutants in the leaves, we use as a proxy the evaporation rate, because I will explain now why. But so it's a good technique to approach it. Then various ecosystems have been studied. There are two agricultural crops like onion and wheat field. Then forests like a holm oak forest near Rome, and a spruce beech forest in Bavaria, in Germany. But I did not cite all of them. This is a map where we made measuring campaigns over Europe, over mainly Southern Europe, Spain, Italy, Southern France, Southern Germany, and so. So a little bit more detail about the tower in ISPRA itself, the institute where I worked. We have a 37 meters high instrumented tower for eddy covariance and other kind of measurements. It's called Atmosphere Biosphere Climate Integrated Station and is still in operation now. And the measurements are used in air pollution studies and so on. So this is a map where Okay, this is a map. The tower is here. There are some interesting features because the topography is quite complex, and from the point of view of mesoscale meteorology, it's interesting because you have very frequently a mountain breeze circulation from north to south and south to north, because there is the tower is located along the Ticino River Valley, which is drawn here, and it's a very long valley. It's like a tube. So there are a lot of channeling effects for the wind. Then we have also the North Föhn phenomena, which are equivalent to the Chinook winds here in Colorado. Then there is the city of Milan, which is an important emission source, and also here the dark area is dark because it's underwater, because there are rice fields who are immersed, of course, and this is, of course, an important source of methane. So the studies can be, oops. Just a minute, please. So using the eddy covariance method, we can only measure the total ozone flux, for instance. But what is important if you study the effect on vegetation is the quantity of ozone which is absorbed, taken up by the plant. And this is not expressed by the total flux, but by the stomatal flux, because most of the pollutant penetrates in the leaves through the stomata, which are small pores on the surface of the leaves. But it is very difficult, it's practically impossible now to measure directly the stomatal fluxes, so we use an algorithm based on the analogy between the pollutants penetration and evaporation, as I already mentioned. And the algorithm makes use of the resistance method. So just to explain rapidly, the fact is, the base of the algorithm is the fact that inside a stomatal cavity, which is schematized here, there is no turbulence. So the diffusion is purely laminar and molecular. And if we remember how the molecular diffusion works, it's characterized by a diffusion coefficient, which is a constant for each chemical species. So there is one for ozone, there is one for water vapor, and they are all constant. So we use the ratio between the molecular diffusion constants of water vapor and ozone, which is a unique number, 1.65. And so we can use the evaporation rate as a proxy for ozone penetration to the plant, to the stomata. But this is, of course, a little bit, I just mentioned this Penman-Mantis equation for evaporation, which gives access to resistances, and they are then converted to the ozone stomatal fluxes. And this is the algorithm. In general, I will not go into the details, but it seems to work because we still need an experimental confirmation, but it's very difficult. I know that there is one group in California which tries to measure directly these stomatal ozone fluxes, but this is still now calculated and compared to the total ozone flux measured by eddy covariance. Now, this is an example of result. Ozone concentration, this is a summer period, day by day. Ozone flux is, the solid line is the total, and the circles is the stomatal, which is always a contribution to the total flux. And is always, the absolute values are less than the total. Then you have the air temperature, the specific humidity, and the heat fluxes, the turbulent heat fluxes, sensible and latent. And as you can see, since it's summer, there are sunny days, so the situation is very stable. More or less one day resembles another one, but the ozone concentration is going up because it's a long period of strong insolation. The fluxes are more or less the same from one day to another. Temperature is going up, and the fluxes, the heat fluxes seem to be more or less the same. In winter, the situation is completely different. There is no regularity because of the changing weather. Sometimes you have north winds, sometimes you have south winds. The mountain valley breeze seems to disappear almost completely. When it rains, like here. This is rainfall. The heat fluxes, the sensible heat fluxes seem to be negative, but I think we cannot trust that kind of observation because in these cases the rules of micrometeorology doesn't hold practically. Then we have another aspect, which is the föhn, so the Chinook phenomenon for these 2 days when the wind blows from the Alps going down in the valley, and where your ozone concentration practically doesn't follow the day-night cycle because there is strong mixing along the day, and this ozone is rather high because it comes from aloft where there is always more ozone than in valleys. This is just to illustrate. This is a typical picture of a föhn day. So these are a summary of observations for 3 years. You have the ozone concentration, the temperature, then the fluxes. The total is here negative, and I multiplied by -1 for the stomatal ones because so you see better what are the data. Then this is also we calculated some average days by season: spring, summer, autumn, and winter. And as you can see, of course, in winter there is practically no ozone flux because there are no stomata. Oops. I did not speak about the. No. Sorry. Now, since the final goal is to assess the risk for vegetation due to ozone pollution. So there are 2 methods which are used now in Europe and maybe in other countries, which is the AOT40 and the POD. The AOT40 is based on the routine concentration measurements of ozone, where you put the limit, you set a limit at 40 ppb ozone, and you make a sum of hourly values measured of ozone -40. Because, why 40? Because somebody considered that below 40 ppb, there is practically no damage on the plants. But this is, of course, a very crude hypothesis, very raw, and we are not sure that if this works. So, but this is recommended by European Commission recommendation to measure. So all the states, the member states, have to measure the AOT40. Now, the new tendency is to use the POD, phytotoxic ozone dose, which is based on the time-integrated stomatal flux over one season, one growing season, I would say from April to October. So this is defined by this integral due to the absorption of ozone by the stomata. And this is, the tendency is to replace the AOT40 by the POD. So we constructed, for the 3 years I showed before, the cumulative curves for the AOT40 and the POD. And you can see that the tendencies do not correspond very well because the phenomena measured by these 2 parameters are different. AOT is based on concentrations, but if you have a high concentration of ozone, but no stomatal uptake, you won't have a damage. Of course, instead, if you have very active stomata and few ozone, you can have more damage. And in fact, in Southern Europe, the damage is not very strong because there is drought and penetration of ozone into the stomata, even if the ozone concentration is high, is not that not that strong. Instead, we have more damage in Northern Europe, where you have very humid, wet forests and very few ozone in air because there is low insolation. And so these results are the contrary of what you could expect. And that's the main reason why we should shift from the AOT40 to the POD. Then a few words about the subflow measurements. I will not go into details, but as you can see, the cycle of sensible and latent heat flux is very similar to the cycle of the subflow, because of course latent heat flux, so evaporation, evapotranspiration, and the subflow reflect the same phenomenon, which is the ascent of the water along the trunks. These are 2 days of the campaign, which took place near Rome in the Castelportiano forest. And but it still has to be analyzed better because the proportionality is not perfect, because you have a kind of hysteresis cycle because due to the delay caused by the ascent of water through the trunk, which is not instantaneous, of course. So you have that kind of cycle like in magnetism. So now we will speak a little bit about stationarity. Can we trust all eddy covariance measurements? No, because one condition for the quality assurance of eddy covariance measurements is the condition of stationarity. So samples should be reasonably stationary regarding mean values and variances. So we are trying to establish criteria to discard non-stationary samples. Now we developed about 4 kinds of criteria: relative stability criterion, cumulative covariance linearity index, and then the difference between covariances obtained using block averaging and running means. And then the last one has been established by Fouken and Vichura. Now, to explain, if you have, this is a curve, a cumulative curve of the covariance for ozone. It's going down because, of course, ozone is going down. And so we draw a linear regression. So at the end of the integration period, you obtain the covariance. And this is this function which is shown there. And if you draw a linear regression through the function I, we calculate the standard deviation, and the RC is defined like this. So it's the standard deviation multiplied by 2 and divided by the final covariance. Okay, then the second one is a little bit similar, but not completely, because it's based on you consider this curve as a series of scattered points, and we calculate their correlation coefficients, and we obtain this CLI. Then the last two criteria are based on a normalized difference between covariances calculated by the conventional method using block averaging and some kind of running averaging. And this is just to show, this is a 25-minute series of temperature, instantaneous value, and you use a resistor capacity damper to filter the fluctuations, and you obtain this kind of curve. And if you calculate that, you obtain the criterion. This had been used by Macmillan in the past. The method is abandoned for measurements, but it can be used as an indicator to detect the non-stationarities. Because the difference between the covariance obtained by this filtering and obtained by block averaging can be considered as a measurement of non-stationarity. And this criterion is very similar to the one which has been introduced by Faucon and Vichura in Germany. And as you can see, it's very similar to the other one, because they divide the integration period in sub-periods, and then they see the difference between the two. So now we use this criteria to study two solar eclipses. One took place in Turkey. I wrote it in Turkish, Tam Güneş Tutulması, which means total eclipse. This is the trajectory of the eclipse. This is a nice photograph of the corona of the sun. This is another photograph with the protrusions. Now, some results. You can see, of course, that the temperature is dropping a lot by, I think, 3 degrees, maybe. And the turbulence practically disappears during the total phase of the eclipse. Then you have the vertical wind, which is quite turbulent before the eclipse. Here, during the central phase, it's very calm. And now what's interesting here, these are the curves of the integration which yields the covariance. These are half-an-hour periods. And if when this curve is quasi-linear, that means that the situation is quite or almost stationary, like this phase before the eclipse and this phase after the eclipse. And as you can see, during the eclipse, of course, the linearity of this curve is completely non-existent. And this is the basis of the calculation of this stationarity criteria I spoke about. And now, this is the result of the calculation of this criteria. 3 criteria are shown here. These are 2 hours during the eclipse, before the eclipse, the central part of the eclipse, after the eclipse, and you see here 2 spikes which correspond to the transition period between light and darkness. And practically all 3 criteria which are represented here undergo strong maxima during these phases of non-stationarity. Now, I calculated the spectra and cospectra during of turbulence during this sample is during the peak of non-stationarity, so the transition period. And you can see, not very well, but you can note, this is the Kolmogorov curve of the inertial region of the spectrum. And normally, if you have a spectral gap, this should drop to 0. And this indicates these values here at the left part of the spectrum indicates that practically the spectral gap disappears because of non-stationarity. And this shows you the central phase of the eclipse, where you see that there is this drop. Of course, the spectrum is not, I should extend the spectrum to the lower frequencies, but I did not do it yet. But it's, I'm sure if you plot the spectrum with the lower frequency part, you will see that the appearance and the disappearance of the spectral gap, which is also an indicator of non-stationarity. Then we use also another eclipse, which was total, but total in the Arctic Sea. So my colleague could not measure it because to make measurements on a boat is impossible because of the movement of the boat. So they used the eddy covariance system in northern Finland, where the eclipse went to 80% of the. This is the trajectory of the eclipse, which was really on the Boreal Sea, but the measuring spot was here, so not so far from the total phase. Now, these are the curves I showed you for the Turkish eclipse. You see that before the eclipse you have these linear accumulative curves, which are the expression of this formula. And this is the central phase of the eclipse, where of course the fluxes, because this is made on the heat fluxes, the sensible heat fluxes, and of course the fluxes are negative during the total phase. But you see the non-stationarities quite well. And this is the result of the calculation of the criteria, which is not that clear because, for two reasons, because the eclipse was not total. And the second aspect is that there were some clouds during the eclipse. So there was some instabilities, but you always see the very flat, not very, but the drop of the criteria during the central phase of the eclipse, and the spikes. There are two spikes here. There are other spikes due to probably passing of clouds and so on. But it seems, I would say that the results are more or less similar for the two eclipses. This is another example, but I tried to see whether there was a non-stationarity episode during a Föhn event along the Lake Maggiore, so where we have the tower. But all these criteria seem to be rather low, because my interpretation is that the Föhn wind is very turbulent, but not non-stationary, because there is a lot of mixing during these phases. Instead, 2 days after it, when the Föhn disappeared, and you have the valley mountain breeze situation, you have a spike here, because when I examined the data here, the wind direction changed completely around this time. So now, since we have several stationarity criteria, which one should we choose? And are they related to each other? So we tried to make a scatter diagram between the DAV and the CLI, but the correlation is poor. So what now? We should remind that the criteria work on a yes or no basis. Data can be kept or rejected. So if we look at the periods when data are kept or rejected by these two criteria, more or less they correspond. This is a series of measurements which had been made on an onion field. And as you can see, of course you can put a threshold which is different for the two criteria, but this is only numerical. But you see that you can eliminate more or less the same periods for non-stationarity. And as you can see, so this curve is the heat flux, the total heat flux during a period. You eliminate it with the CLI and you eliminate it with the DAV. And all these periods more or less corresponds. That means that these criteria seem to be reasonable. Okay. Now I come to a provisional conclusion because the work is not finished. So we made an analysis to try to establish criteria for the elimination of non-stationary samples which occur in eddy covariance work. The non-stationary samples introduce biases in the results, mostly due to low frequency fluctuations, which in theory do not contribute to turbulent fluxes. But some people say that in reality there is a contribution. It's also a kind of flux which is originated by low frequency fluctuation. But this is a question which is still under discussion. Then the problem is of course related with the basic assumption of micrometeorology, which is the Reynolds separation between low and fast fluctuations occurring to atmospheric variables. And this is also related to the presence of absence of a spectral gap. So this work is continuing, and thanks to the cooperation of these three people, Professor Scaes from Louvain, Belgium, Dr. Famulari from Bologna, Italy, and Professor Gerosa from the University of Brescia in Italy. And thank you for your attention.
Thank you, Stan. Let's see if we have some questions, either from the room or from the Slido. While we wait. So can you specify, so stationarity is derivative of something with respect to time equals 0. I'm a little not sure what's the something you're looking at.
What was the?
So what needs to be stationary for your assumptions?
Normally there are two criteria, two elements, which is the stability of the mean and the stability of the variance of a variable. So these are the two criteria defined by books, textbook in statistics. But of course, nothing is objective in that definition. There are also other criteria, but the question is still under research.
Okay, because in some examples you use windows, for example, and is this method dependent on the window you pick and on the time response of your instruments, for example, or no? Okay. Okay.
No, the time response is very short. Most measurements were made with a 10 hertz frequency. So we resolve all the micrometeorological fluctuations. So it has nothing to do with that.
Okay. Okay, nothing from the Slido, not much from the room. I'll say to thank you once more.
Thank you.
For the interesting talk.
Thank you.
We have a Slido question. Are we still in time? Okay. So, there is no way to correct the non-stationarity periods to perform eddy covariant measurements. Justin. Justin asking if there is a way to correct for the non-stationarity. Answer is okay.
Non-stationarity is a natural phenomenon, so you cannot eliminate it. It's a natural phenomenon, non-stationarity. So if you change the data, you destroy data, I would say. So it's better to eliminate or to study the influence of low frequency fluctuations, which is still a problem.